Okay, now we have one more circuit change to make, one more modification to make to this, and it's going to consist of two steps. But the modification is this. Now that we have our signal current from the motor coming through here at the proper timing and things, that advances the voltage at the output here, causing a voltage increase over to here. However, now we have a passive resistance here that's necessary to drop a voltage across this so that we can have a signal coming out here, and also to drop the voltage for the motor to run under normal conditions. But that resistance now is going to buck against any change in voltage output here, because the resistance of the motor was, I measured it under no voltage across it, winding resistance with an ohm meter, and it's around 15 ohms, and we have a 100 ohm resistor here. So this resistance would have to go down below 15 ohms in order to get any kind of a voltage just to match the 6 volts here. Now I am not going to design this to put a voltage match across the motor under stall conditions, because that would require a whole change of values and using power resistors. I don't want to use power resistors. I just want to do a demonstration of just the concept of this. However, though, as we're saying, this here passive component here will not work in the application that we need to do, and that is to keep more power to the motor output when it's necessary. So in order to do this, we have to have the resistance change under a demand for more current for the motor to have to it. So a passive resistance will not work, so now we have to use, once again, another active component that will switch in, just as we did down here, and that would be another transistor. So now Q9 will replace R5X, the 100 ohm resistor. Okay, now Q9 is going to have just a little bit different function than what Q8 did. Q8 was a voltage controlled switch. Q9 is going to be a voltage controlled increase in current when called for. It's going to be a variable resistance. Instead of a switching component, it's going to vary its resistance under demand load from the motor. So the way I have this in here is, again, this is probably looks like a common base configuration, where the base voltage is set by the main supply voltage coming in to keep a steady base voltage here, and it's biased into its linear region so that the current through the motor can flow through here readily, and being in a linear region, it has the ability to go down or up as necessary according to the base input. Again, the way I got the resistor values was the same way I did before. I just used Ohm's law. I just again took 1/5 of the collector current that would flow for the divider current, and then just used the supply voltage and the drop at the base here, which would be 0.7 volts higher than the motor voltage. So this would be at 6.3 volts, and then I would just use those voltage measurements, those voltage calculations, and then just calculate the way I did before the Ohm's law to get these resistor values here. And anyway, it ends up with a grounding resistor, pull-down resistor about 1.3K, and a pull-up resistor about 1.8K to put about 6.3 volts at the base here, roughly, and to put this in its active region. Okay, let's go ahead and build that, and then we're going to test that and make sure that we're getting around 6 volts here, and keeping our mainly that we have 6 volts to the motor, and that means that we have this bias properly. And if it's not, then we can always adjust these values until we get 6 volts to the motor. And we're going to do that next, and then we're going to design the last part of this this modification to make this into an electronic variable resistance, and that will be next. But let's go ahead and build this part first and get that functioning. After watching my preview here, I realized again I kept on saying 6.3. It'd be 6.7 volts at the base of the transistor here. That's 0.7 volts higher at the base than it is at the emitter. So now we have it at the proper thing here. So 6.7 volts is the base voltage of Q9. Okay, I still have this resistor in here because I want to take a voltage measurement across the motor here under a stall condition and see what that voltage drops down to. Then when I put Q9 in there, I'm going to do the same thing, and I'm going to make sure that we're getting the voltage drop across the motor doing the same thing. So now I have my voltmeter on the motor side, and I'm sitting at 6 volts, and I'm going to stall the motor now, and it drops down to 1.8 volts. So we're going to record 1.8 volt drop with the resistor in place. Okay, I'll remove the 100 ohm resistor. Okay, here's transistor Q9 right here, and its bias circuitry. And we have the voltmeter connected up here to the motor, and we'll hook it up now. Across the motor we got about 5.8 volts, close to 6 volts. And go ahead and install it. And it drops to about 2.8. Okay, so we're in 2.8 in that area there. So that's showing right now that the feedback is going through here, and because this transistor is no longer a passive resistance, it is allowing more current to flow, that we're getting a higher voltage output across the motor here. Okay, now we're going to do the next part of the circuit, and this is still acting as a series dropping resistor right now, resistance, but now we're going to change this now into a variable resistance with electronic signal, and that's coming up next. So we're up to this point here right now as a variable, as a series dropping resistance active, and now we're going to change that into a variable resistance that will be electronically controlled, and that will be the second part now of this here design. And that brings us to the last modification now of this circuit. And I'll explain how this works. This is transistor Q10. It's going to act as a voltage controlled current switch, just as we had down here. This is going to be biased in the cutoff region so that it has no influence on the base of this transistor here during normal motor running conditions. When the motor begins to stall, we get a signal back into here, and then this here, the base of this transistor now is going to be coupled to the output of the regulator, so that when the signal from the motor comes into here, the voltage output of the regulator goes higher to here. It's also going to send a high signal to the base of this, causing this transistor to start conducting. When it starts conducting, it's going to put a parallel resistance smaller than this here across the base of this transistor here, causing this resistance, total resistance, to drop, allowing the positive input to this base now to rise. And when that rises, that's going to allow this transistor to run harder and source more current to the motor and cause the motor voltage to output to increase as the motor demands for it to. So now we're going to put the Q10, its bias circuitry now. Okay, I have this here transistor and its bias circuitry in here. It's biased to be close to cutoff, just below cutoff a little bit. And I have this wire out right now, the feedback wire, but I'm just now going to get ready to put this wire in here now, and we'll see how that is. Okay, so I'm putting the wire in there now. First of all, here's the voltage of across the motor without the feedback wire. Now I put the feedback wire in here, and the voltage across it went about maybe 40 millivolts, if even that. All right, so now there's the voltage across the motor. Now I'm going to stall the motor. There's the voltage across the motor now. It starts out like this. I stall the motor. It drops to there, 5.7 volts. Without the feedback, it dropped to 2.8 volts. With the feedback, it went to 5.7 volts. If I decrease, now by using a variable resistor in here, a trimmer, I can reduce this resistance even more for the feedback to make this more sensitive and get a higher output voltage. But this here demonstrates the concept of this circuit working this way. So under normal running conditions, this transistor is on, linear, and this transistor is off. And that's what we have right now, 6 volts across the motor. But when I stall the motor, this here transistor begins to come on and puts a positive voltage to the base of this, and causing that to increase in output to drive the motor harder and cause the voltage to rise harder. And so when I put the stall on, it increases farther. Okay, so that's what we need is the design works properly with feedback. So the motor feedback goes into here. It causes a signal to cause this transistor to come on harder by 2 signal voltages here. Okay, so that was the a proof of concept to make sure that this circuit would actually work under this here kind of design changes and things, and it works properly. And we'll see what's next on this now. Okay, so in conclusion, we started out with a very simple circuit here, which was just a simple transistor voltage regulator, and then had an idea of what we wanted to make it do. Went through all the design modifications to end up with this circuit right here. And it was enjoyable taking step by step through all the modifications and the logic behind each step and each stage of the process of design this here. And I really enjoyed doing this here, and I think so how my electronic video is going to be is going to be just a demonstration of the circuit design principles, how I come up with my designs and everything, just for the enjoyment of watching, and it's maybe educational for those who are just learning how to do transistor circuit designs as a hobby level. And I really enjoyed doing this video, and so thank you for watching. Bye for now.